so I think I'd like to get started, yeah? Let me remind you that Jean Bourgain will give a talk after Enrico at about 5 o'clock. So we've added in that talk, and there's ample time before dinner. So don't leave immediately after Enrico if you want to see Jean. Okay. The theme of the afternoon's talks is in number theory, and I can tell a little story. In the 1980s, mid to late 1980s, John and I were both visiting Caltech, in fact, both visiting Tom Wolfe, amongst many other people. And we spoke quite a bit. And at some point, he was moving, he'd worked in Banach spaces and harmonic analysis very effectively, but it was clear that he wanted to broaden his horizons. And as we know, he did that dramatically in many, many different fields, as we'll see at least some of them in the next few days. So he comes up to me and he says, can I suggest a problem to him? Actually, he put it slightly different. He says he wants to score in number theory. That's how he put it. So I said, you don't score in this, but let me suggest a problem after some thought, given his background and his amazing strengths. And I suggested he look at a problem of Montgomery about estimating LP norms of Dirichlet polynomials that essentially had seen no progress for many, many years. And I didn't hear back from him for a couple of years. Now that I know him very well, I know that that's a long time, because usually it's 3 days and you've got a complete solution of your problem. But he did come back with two remarkable insights. The first was that the conjecture was false, which is plain false. It's true that it was in a subtle thing and you had to reformulate it, but it's amazing that previous people had not noticed it was false, including me, who'd given him the problem. So he fixed that up. And the second he observed was that the conjecture, if true, implied the solution to the Kakeya problem, which at that time was not so popular. He was getting, certainly Tom Wolfe was interested in it. And that was quite a remarkable insight. And we know that problem still resists all efforts, but these conjectures of Montgomery implied that. These conjectures of Montgomery they still are really connected to the Lindelof hypothesis and problems of that nature. And I sort of secretly, when he said to me, well, it implies Kakeya, and I thought, yes, of course, the number theory is the hard stuff, and the harmonic analysis is the easy stuff. That's the way this is going to go. But over the years, he's proved me absolutely wrong over and over again as he gets into more mainstream number theory, and we'll see it over and over again, solving problems using combinatorics, using harmonic analysis, using whatever available, and very often inventing tools and techniques. I would say he's not just a problem solver, he's actually a theory developer. And just as one example, so 27 years after this discussion with him, he and Nigel Watt, using the L2 decoupling theory that he developed with Demeter, have given the world record on the bound for the Riemann zeta function on the half-line. So he carries that record. It's a very tiny advance. And the actual advances in this L2 decoupling have many more interesting applications at this point, and we'll hear some of them, I hope, tomorrow or the next day. He's really changed with each time he solves a problem, almost every paper he writes, and as you know, he's written a tremendous number of papers. In fact, I think it was Gumbert who was the idea behind this conference, and more or less it was, well, he said, when I've published 500 papers, then you can maybe run a conference. I think he's well beyond 500 at this point. But each of his papers has a major idea, and many of them have very long-lasting techniques. Okay, so with that background, let's get on with our lectures this afternoon. And the first speaker this afternoon is Alex Kontorovich, and he, together with Jean, have advanced quite dramatically the theory of Diophantine analysis of affine linear actions of groups and semigroups. And the theory relies on many of the fundamental tools that John has developed, some of which you heard of this morning. And that's Alex and Kontorovich and Jean, have made a number of far-reaching further developments in this theory, which have many classical applications. And from the title of the talk, I suspect you'll see some of them. So our speaker is Alex Kontorovich, and he'll talk about thin groups and applications.
Well, thank you, Peter, and thank you to all the organizers. It's an incredible opportunity for me to be here, and I'm deeply honored. As Peter said, John and I have worked quite a bit. I think at last count, maybe a third of my papers are with John. We have a dozen papers or so. And he's had just a tremendous influence on me mathematically and in every way. Sometimes I'll go to a place and someone pulls me aside and says, you work with Jean a lot, right? I said, yeah, we have some paper. And they say, how do you do that? Because, isn't he scary? Isn't he too fast? And I said, no, he's a sweetheart. He's always, treated me perfectly well and like an equal and everything. But the honest truth is when we first started working together, I was deathly afraid of him. Jean, maybe turn off mute your camera for a second. I remember when I had some idea and some proposal I sent here, and he sort of pulled me aside at tea and explained to me how to do what I was trying to do. And so we wrote, that was our first joint paper, and in fact, I remember at some point running to Peter for help because I really felt paralyzed. We're in there, we're at the blackboard, and we're talking, and I don't know what to do because I have these ideas, but I know they're stupid, and I'm trying to race ahead to try to keep up with him. And Peter gave me the best advice ever. He said, what are you worried about? That you're not as good as Jean? You're not. Nobody is. You're in good company. And since then, it's been an absolute, now I can say whatever stupid idea comes to my head, and then I don't feel bad. Jean never, told me, you're an idiot, I don't want to talk to you anymore. So to those people who ask how you work with John, don't worry about it. You're not as good as him, and that's okay. And anyway, so that's my story about Jean. Okay, so I wanted to talk a little bit about some work we did in thin groups and applications. Let me spend a little bit of time reviewing one very particular instance of this. Some of you have heard this many times, but just in case people haven't, let me go a little bit through the theory of Apollonian circle packings before I get to the things I really want to talk about. So just to remind you, there's an old theorem of Apollonius from 2,000 years ago that if you're given three mutually tangent circles, as shown here, or actually any three circles, the problem is how to construct further tangent circles that are tangent to the given ones. And in this case, this theorem says that there are exactly two that you can place tangent to the given ones. And that's the theorem, and he did it with straight edge and compass. Or so we're told by Pappus. Actually, his work on this does not survive, but Viet managed to reconstruct the proof, which is indeed a straight edge and compass proof and uses tools available to Apollonius, so we have no doubt about this. Okay, so once you do this once, Leibniz observed that what you're really doing is inscribing circles in curvilinear triangles. And so why not do it again? He's studying limits and so on, so he starts doing it again and again and again. And he's actually the first to make this fractal, but in the 1950s, the credit is somehow given back to Apollonius. So these are now called Apollonian circle packings. A further breakthrough was made by Frederick Soddy, who made another stunning observation that somehow everyone before him had missed, and that's the following. Let me label the circles by their curvature. So the curvature of a circle is 1 over its radius. So this is a circle of radius 1 over 18, 1 over 23. This circle has radius 110, but I want the interiors of the circles to be disjoint, and so I'll give it the opposite orientation so that its interior is actually its exterior. And then what happens when you add more and more circles, just as we did there? Let's keep track of the curvatures. Now this curvature is 35. That curvature turns out to be 37, so there's a circle of radius 1 over 37. And when you do the next round, there's a 63 and a 340, whatever that is. And you do this forever, and the miracle of miracles is that all of these numbers are in fact integers. So that's something that arguably Apollonius could have been aware of, but somehow evaded him and everyone since him until Soddy. So how could this possibly be? Where the square root of 2 or pi or something? Why are these numbers coming out integers? So what Soddy had rediscovered is an old theorem, actually originally due to Descartes, who had a mistake in his proof, but never mind, we'll give it to him anyway, which states the following. if you have not 3 but 4 mutually tangent circles, then their curvatures satisfy a beautiful algebraic relation. The sum of the squares of the curvatures is almost the square of the sum, off by a factor of 2. And what this means is, if you're given 3 curvatures, K1, kappa 1, kappa 2, and kappa 3, well, now you have a quadratic equation for kappa 4. Quadratic equations have 2 solutions. That means there are 2 circles that are tangent to 3 given ones. That's the Apollonian theorem in algebraic guise, and here's that 4th circle. Now, it's an easy exercise that the 4th curvature is related to the 5th curvature, this new curvature, this other solution to the Apollonian problem, is related to the curvatures of the others by this simple algebraic relation, which you derive immediately from the quadratic form. And it's similar to a Viet involution, so let's call it that for a minute. And the important thing is that the coefficients here are integers, and all you're doing is adding, multiplying, and subtracting numbers. And when you do that with integers, you get integers. So it's an integer linear combination of the previous curvatures. But every curvature, every circle in this packing is obtained from the previous one. For example, if I want to put a circle here, I treat C1, C2, and C4 prime as fixed, and then I translate C3 into that region. And these are the 2 solutions to the Apollonian problem in that configuration. And again, every time you do this, this is what Soddy observed. Every time you do this, if you happen to start with all 4 being integral, then the rest will all be integral. Okay, so that's this observation. And we did indeed start with integers for the first 4. And once we have 4 integers, the rest are all integers. It's not true if you just start with 3 integer curvatures. On the next step, you might get some square roots. Okay, so once you have a picture like this, and you're a number theorist, you start asking number theoretic questions. Who are these numbers? And somehow it took another almost 100 years from Soddy to this beautiful series of papers by Graham, Ligarius, Mallows, Wilkes, Yan. I couldn't fit all their names on the slide. Which numbers actually arise? So let's let K, big K, be the set of all curvatures of circles in the packing. Let's just fix this as our packing. There are infinitely many of these integral Apollonian circle packings. So the curvatures are -10, 18, 23, 25, 35, 47, 62, and so on. And they made an immediate observation that if you start reducing these mod 2, mod 4, mod 8, mod 3, mod 9, and so on, you observe that the only curvatures that you'll get mod 24 are this list. And in Elena Fuchs' thesis, she explains what the number 24 is doing there, and it has to do with the failure of strong approximation for small primes. I mean, there is strong approximation, but not at every prime and not at every prime power. So she completely clarified the nature of these local obstructions, and so we'll define an integer to be admissible if it passes local obstructions, if it lies in one of these residue classes, mod 24. And so what's the natural local global conjecture? Again, already initiated in this paper and clarified even further in a paper of Fuchs and Sandin. Every sufficiently large admissible integer should arise as a curvature, should arise in this picture. Okay? Now, you've certainly needed sufficiently large because, well, 2 is admissible, but there's no circle of radius 1/2. It would fill up the whole board, right? So you need to go some distance in, and once the integer is sufficiently large, and of course there's this admissibility restriction, then they should arise. Okay, and the work with Jean that Peter was referring to, some of it anyway, is that we have this theorem on the local global conjecture. We can't prove the whole thing. We can't prove that every sufficiently large number arises, but almost every admissible number does arise. In the sense that if you look at how many curvatures you have up to x, relative to how many curvatures you should have up to x, how many admissible numbers, that ratio goes to 1. And this builds on a lot of other work. Already some ideas in this original paper go into this. A very important contribution is by Peter himself, who wrote a letter to Ligarius clarifying the exact role of thin groups and what can be done. There were some improvement on Peter's estimates by Fuchs, and then finally Bourgain-Fuchs showed that this ratio has a positive lim-inf. So that's the positive density conjecture, and then finally we showed density 1. Okay, let me just briefly sketch some of the ideas going into this proof. So the first thing you might ask is, well, I said every sufficiently large number which is admissible should be there. Why? Who says? What's the rationale behind that idea? So why should every large admissible number arise? Let me give you a heuristic for it. So let's count not curvatures, but circles. In other words, curvatures with multiplicity. How many count all of the circles in the packing whose curvature is at most some growing parameter x? And if you plot this function, well, you'll see very clearly it grows faster than linear and slower than quadratic. And in fact, it's a result of Hio and myself that it grows at this asymptotic rate, where that number is a universal constant. It's the Hausdorff dimension of any Apollonian circle packing. And so what's the heuristic? Well, let's say you have you have this many integers up to x. And so if you have a typical integer of size x, which is admissible, how many circles should have that number as its curvature? What's its expected multiplicity? Well, the total multiplicity of all numbers is this, and you have a 1 over x chance in hitting that particular integer. And so that's what you expect the multiplicity to be. And of course, that number goes to infinity as x goes to infinity. So that in particular, the multiplicity should be at least 1 once the number is sufficiently large, which means it should appear. Okay, so that's the very naive, just counting argument that says the local global conjecture should be true. And the way to prove this theorem, well, we use the circle method. And what we show is that we can't show that the multiplicity is individually this large. That would prove the whole conjecture. But we show that on average, the multiplicity is as large as it should be. And that extra averaging is what lets us prove something, and at the cost of weaker results. So we don't get the whole conjecture, we just get a density 1 statement. The organizers are very good, because exactly the tools that go into this are expander graphs and the super approximation theory that we heard about from Alireza, which itself uses some product from the first talk of the morning. We have to do some more, so we have to create bilinear forms and bound some exponential sums and prove equidistribution in cosets. So there are a number of ingredients that I don't have time to get into. But if you want to read a little bit more, there's a survey from A to Z in the bulletin from a few years ago that discusses some of these things in more detail. Okay, any questions on this very quick sketch? Yes, so in L2, in fact. So what you do is, the way the circle method works is it decomposes this multiplicity into a main term and an error term. And the main term should be larger than the error term. And we can't prove that individually. What we can prove is that the L2 norm of the error term is little o of what the corresponding bound should be. Okay, so that's what I mean by on average. There's an L2 instead of an L infinity calculation there. And that's why we can prove something, but that's also why we can't prove the whole conjecture by those methods. Any other questions? Feel free to interrupt at any time. Okay, so what I haven't told you is, actually it'll be important for what I want to say to explain a little bit about the proof of that. So let me sketch that proof. If you recall this picture with these Viet moves, where we just kind of topologically thought about this circle reappearing there, and we thought about the algebraic relation, actually there's a completely geometric and very simple geometric action, which is, let's call this dual circle C4 tilde. So it's dual to C4 in the sense that it goes through the 3 points of tangency of C1, C2, and C3. And the simple observation is, if you reflect, if you invert in this dual circle, then it fixes C1, C2, and C3 and replaces C4 with C4 prime and vice versa. Okay, and if you do this with the other circles as well, so here's the dual to C4 circle, the dual to C3, so C3 can get moved there, and C2 can get moved there, and C1 can get moved into here by this dual action. And if you take the group generated by these 4 reflections, you actually get, in the limit, the entire packing. And so this group generated by these 4 dual reflections, you should think of not as a Mobius group just acting on the plane, but this idea going back to Poincaré that you should extend things to the upper half space. So think of it as isometries of upper half space, which means now instead of circle inversions, I should think of geodesic hemisphere inversions. And so if I start with a point here, I invert through C4 tilde, then I invert through C3 tilde, and so on, and all these points are getting closer and closer to the ground, and the set of limit points is in the ground, is in the boundary, and that's exactly this packing or its closure. Okay? So the structure of that group is what's really responsible for these counting theorems. And the key to proving the rest of the theorem I won't go into, but it uses an idea going back to Sarnak equidistribution of low-lying horocycles. Now you need low-lying horospheres, but in infinite volume, in thin groups, and the spheres themselves are of infinite area, so there are some technicalities. But that's all old news. So the question that I've kind of been thinking about ever since, I mean, there are a lot of miracles that happened in the process to proving that theorem, and I'd like to understand where do those miracles belong? Why do they happen? Why is there this group? Why are there these transformations? Where does the integrality come from? So where does Descartes' theorem come from? Of course, I can prove Descartes' theorem for you. That's not the, there's something more philosophical going on. There are these Viet moves. We get a reflection group. Its limit set is the packing. So what's the general setting for this problem? And so this is what I'd like to propose, a general setting. So here are some definitions. So a packing of the extended Euclidean space means a collection of oriented codimension 1 spheres. So spheres in 3 space, circles in 2 space, and more generally. The orientation, of course, as before, we want to allow the exterior of a sphere to count as its interior. Of course, we also allow half planes, oriented half planes. And what we want, so to be a packing, this collection should have disjoint interiors, and moreover, we want the tangency graph to be connected. Okay, so it's a collection of spheres. No two touch each other, but they're not just out in space somewhere. There's a chain from any one to the other following tangencies. Okay, so that's not enough structure. We will want dense packing. So a packing is dense if it intersects any ball in space. Okay, so it's really filling up, it's actually packing space. Somehow the word packing has many, many different uses in the theory of packings. Now, a packing will be called integral if every sphere in the packing has integral bend. And by bend, I mean 1 over the radius, because in higher dimensions, curvature is, depending on which curvature you mean, is some constant over the radius squared. And I want 1 over the radius. Okay? So I'll stop using the word curvature. I'll start using the word bend. So we would like to understand integral. So infinite, I don't want a circle, a sphere with its interior and its exterior, right? That's a stupid dense packing. I want infinite dense packings, and I want to understand the integral ones. Now, as stated, it's hopeless, right? The problem is wide open. You just stick in any sphere that's sufficiently small, and you keep doing it until the spheres pack space. So that's not interesting. We need a little bit of structure. And here's the key definition. I want to define a gamma packing. So a gamma packing is an infinite dense packing, as defined above, with the property, as in the Apollonian case, that there's some discrete, geometrically finite group of isometries of hyperbolic n+1 space, which is generated by reflections, and whose limit set is our packing, its closure, and the prime is that the packing was assumed to have not just spheres, but oriented spheres, but of course the limit set can't see the orientation. So forget the orientation. This is what I mean by a gamma packing. Any questions on this definition? This is the key. Yes? So the packing is a collection of circles, but there are limit points that are not on any circle. I'm not including the interiors. If I included the interiors, it'd be all of space, because I'm assuming it's dense. So I just want the circles themselves, or spheres, whatever. Any other questions? Okay. And so now, this, I think, is, for me, an interesting problem, let's try to classify all integral gamma packings. So where does this Apollonian packing really exist? Why does it exist? Okay, maybe it looks hopeless at first, but actually it might not be that hopeless, and it might not even be that hard. So this is all work in progress, I should have said, with my postdoc at Rutgers, Kei Nakamura. And the reason we think it's not that hopeless is because we have this packing arithmeticity conjecture. And here's what the conjecture says. If you have one of these integral gamma packings, so the definition says you have a packing P, and if it's a gamma packing, then it has a gamma. So now you have a group as well as the packing. Then what you should do is look at the group generated by your group together with its reflectors at the boundary. I'll explain that in a second. And then you should get an arithmetic hyperbolic reflection group. So let me just explain by a picture, by an example. So in the Apollonian case, we had this group generated by these 4 dual hemispheres, and that's an infinite volume group. And this infinite volume group is geometrically finite, so it has flares. It's just flares that go out to infinity. And when you look at the convex hull cuts out, by geodesic, cuts these flares. And so that's what I mean by the reflectors. So the reflectors of this group are, in fact, the original circles themselves. C1, C2, C3, C4 are the reflectors in this case. And if you take the group generated by all 8 of these circle inversions, what you'll get, it's easy to see, is an ideal octahedron. It's the fundamental group of an ideal octahedron with all dihedral angles pi over 2. And that is commensurate to the Picard group, SL2 of the Gaussian integers. So that's the conjecture. The conjecture is the only way, so if you have some group gamma and it acts on spheres preserving integrality, it has to come from an arithmetic hyperbolic reflection group. Is that clear? So that's the conjecture. And of course, why do I care about the conjecture? So if the pack conjecture were true, it would be very useful because of this beautiful theorem of very many people, beginning with Windberg. There are only finitely many maximal arithmetic hyperbolic reflection groups, and in fact, they all have dimension at most 29. Okay, so this is a result of many people. Nikulin, Long, McLaren, Reed did it for Fuchsian groups, and Agel for Kleinian groups in 3 dimensions, and this collaboration did all other dimensions. So in any dimension, there are only finitely many, and Windberg's theorem tells you there's a bound on the dimension. So that's it. There are finitely many maximal hyperbolic reflection groups. And so that means we have a chance of, if we can prove this conjecture, maybe we can use this to completely classify everything that in some sense resembles the Apollonian packing. Please. Yes, of course. Yeah. Everything uses lambda 1. Yeah. Super approximation is hidden in here as well. Absolutely. Which you should all read Peter's survey on thin groups and, thin groups? Super approximation. Anyway, so it's, or just read the original papers. Yeah. Lambda 1 is key to everything that I'm saying, even though I'm kind of hiding it. Okay. Any questions? All right. Well, if we want to have this classification, maybe we should try to find some examples. So here are the examples of integral gamma packings that were known before we started our work. One was already known to Sadi. We now call it the 4-simplex packing. It's just the analog of the Apollonian packing in 3 dimensions. Actually, there is no analog in higher dimensions once you go beyond 3, because the spheres start to overlap. Even if you have a configuration and you take the same group as the Apollonian group, they start to overlap. You have to do something else. More recently, Güttler and Mallows realized that there's a conformal way not of putting a single circle in every curvilinear triangle, but 3 circles in every curvilinear triangle. And that's now, we call it the octahedral packing, and it was studied by my student Xin Zhang, the arithmetic properties. And the combination of these two is the 4-orthoplex sphere packing, which was studied by Diaz and independently Nakamura. Okay, so these are now 4 examples, the Apollonian and these 3, and a few remarks. So that's basically what was known. So the first remark is, for sphere packings and higher, except for circle packings, even constructing gamma packings, ignoring integrality, is a very well-studied and not so trivial problem. So already Boyd had examples. Maxwell classified these so-called Lorentzian Coxeter systems of level 2, and other people, and that has a lot of applications, for example, to rational points on K3 surfaces, Lorentzian Kac-Moody algebras, things I understand not at all. And another remark is that if what you're really interested in is trying to understand the local global problem, it actually becomes easier in higher dimensions. So this is already observed in my work on the Saudi packing. The expected multiplicity, instead of, the packing here, the Hausdorff dimension of a circle packing is between 1 and 2. These dimensions are between 2 and 3. But you still get to divide by x. So now the multiplicity is x to a power greater than 1, and the problem becomes much easier. So from these 2 points of view, actually the most interesting and difficult case is back to circle packings. And in circle packings, we have very, very many. It's interesting, and so it's difficult from the point of view of the local global problem being difficult. It's interesting from the point of view of it's not hard to construct gamma packings thanks to Kobe-Andreev-Thurston, and then determine which of them are or aren't integral. So let me explain that. Any questions here? Okay. So these are so-called polyhedral and now circle packings. So what's the Kobe-Andreev-Thurston theorem in a form, the details were written down by Schramm even though they were claimed. So let me state it this way. Every convex polyhedron admits, by convex polyhedron now I just mean the combinatorial type of the polyhedron. It admits a geometrization which has a midsphere. A midsphere means a sphere which is tangent to all the edges. So let me just give you an example. Let's look at the cube octahedron. So let me remind you, this is an Archimedean solid. You start with a cube, and you start chopping off the corners. And when you chop off the corners until you get a regular octagon, so this is actually called a truncated cube, one of the Archimedean solids. Archimedean means it has faces that are regular polygons, and it's vertex transitive. So every single vertex has 2 octagons and 1 triangle added. And if you keep chopping a little bit more until you get to the middle, that's a cube octahedron. So now you have square faces and triangular faces, and the pattern at every vertex is square, triangle, square, triangle. And this is the same thing that you would get if you started with the octahedron and truncated the edges to the midpoints. So it's called the cube octahedron. Okay, so the Kobe-Andreev-Thurston theorem tells us it admits a geometrized version with a midsphere. So there's a configuration of these vertices. I mean, it's very easy for the Archimedean ones. This is a general fact for any convex polytope. There's a configuration of these vertices and faces so that the edges are exactly tangent, all tangent to a single sphere, which is called the midsphere. Okay, so that's the theorem. I mean, it's kind of an amazing result that maybe the ancients could have somehow come up with, but I highly doubt they could have, as you'll see. This is a rather important and difficult result. So what does this theorem allow you to do? I claim that it allows us, for any convex polyhedron, to attach a circle packing modeled on that polyhedron. How do you do it? The observation is, once you've geometrized your polyhedron, the midsphere is also the midsphere of the dual. So the dual polyhedron to the cube octahedron, it's called a rhombic dodecahedron. So its faces are rhombi, and there's 12 of them as you go around. You can see, I mean, the faces will be the vertices of the cube octahedron, and there's 4 on top, 4 in the middle, and 4 on bottom, so it's a dodecahedron, 12 faces. And once you see this, you're almost there. You see the faces, every vertex has a circle, rigid circle, and the tangency graph of the vertices, of the circles coming from vertices, is exactly isomorphic to the original polyhedron. And moreover, you have this dual polyhedron corresponding to, which has circles corresponding to the faces of the original polyhedron. So this gives us 2 sets of circle clusters, one whose tangency graph is the original polyhedron, and the other, which is the dual. And after stereographic projection from the sphere, you get a configuration like this. So the blue circles and lines have a tangency graph, which is the cube octahedron. So we should see at every vertex triangle, square, triangle, square. So let's see. Here's a triangle. So I'll look at this vertex. Let me look at that vertex. Sorry, a vertex is a circle. A vertex is a circle. So let's find a circle in here. I should have practiced this before, huh? So let's look at this circle. It has a square over here. It has a triangle there, and a square there. Okay, so it goes triangle, square, around this circle. Okay, so the tangency graph is that of the cube octahedron, and the dual graph is exactly this. And that's, by the way, exactly the reflectors. The dual graph, reflections through the dual cluster will be our group of isometries of hyperbolic space, and it acts on the original cluster, and that's what we call a packing modeled on a polyhedron. So any questions on this construction? So in dimension 2, constructing circle packings is trivial, these infinite packings. The question is, which of them are integral? So now I can call a polyhedron integral if there exists a configuration, if there exists packing modeled on this polyhedron, which is itself an integral packing. Now we have infinitely many guys to look at. When we were looking at higher dimensions, there were only finitely many possibilities. Now we have infinitely many, and the problem is to classify these. Okay. So let's try to classify the integral polyhedron. Now, if you give me a polyhedron, what does that mean? You've given me some list of vertices. You've given me a list of edges and faces, just combinatorial data. Even running the proof, the Kobe-Andreev-Thurston proof is, it's an existence proof. And so geometrization is itself a difficult process. And so Stevenson has these circle packing software to do it, but I think his only works if the polyhedron is triangulated. More generally, it's even more complicated. I could be wrong. Maybe he can do the general case. But it's this infinite numerical process that achieves geometrization. And that's, can you tell if 5.99998 is 6? It's not so easy. But to the rescue is rigidity, Mostow rigidity, which actually in this case, Peter tells me is already due to Selberg. And what it says is that you can make not just the bends, all the curvatures, and all the centers algebraic. Now that's beautiful for trying to determine if 5.99998 is actually 6. Because what you can do is you get a whole bunch of decimal places, and then you guess is there a nearby algebraic number. There are algorithms to do this. Once you guess the values, you can rigorously verify that you have the tangencies correctly. And the process halts. Okay? So this is how you take this infinite limiting process and turn it into a finite computation. Any questions on that? Yes? So a priori, I don't know how to bound the degree in terms of the complexity of the polyhedron. Presumably there is some, but not that I know of. And yeah, so yeah, the answer is I don't. There should be some bound. The degrees should be controlled somehow by the complexity. I don't know how. There exists, that's right, there exists a realization which has all curvatures and centers algebraic. Okay. That's not all. There are more difficulties. So here are some more difficulties. Difficulty 1, well, if you want to classify them all, we've found infinitely many polyhedra which are integral. Now, if you find infinitely many, it means you have a construction, right? The construction is, well, part 1 is an immediate corollary of part 2. There are infinitely many distinct polyhedra which actually give you the same packing. the same limit set. So you can realize the Apollonian packing not as just this one group gamma, but there are infinitely many discrete reflection groups gamma whose limit set is the same circle packing. So that tells you that there are infinitely many integral polyhedra. And moreover, there are infinitely many non-isomorphic integral circle packings. So there are infinitely many circle packings that are integral. Okay? So in this sense, the classification seems kind of in trouble, but it's not, because the proof of all of this is some double and gluing construction. There's some construction that takes an integral polyhedron. You can double and glue along a face. That gives you a different circle packing, but it's built on the same underlying structure. And what's going on is that the reflection groups being constructed here are just non-maximal. And you can, there are also examples of this by Alcock in higher dimensions. So from that point of view, maybe this isn't something that you should be worried about. Okay, and now, so here's the theorem. And this is a complete classification of integral convex polyhedra. It's exactly what I wanted. So obviously I'm missing something. I'm missing the word uniform. So we haven't solved the whole problem, but we've classified the uniform. So uniform, again, means the faces are regular polygons and it's vertex transitive. So these come in three categories. There are the Platonic solids, the Archimedean solids, and two infinite families, the prisms and antiprisms. And so we have a complete classification for which of these polyhedra are integral. And it goes like this. So for the Platonic solids, you have the tetrahedron, which is the classical, which is the Apollonian gasket. You have the octahedron, and that's what I meant when we were discussing the Güttler-Mallows and construction, which my student Xin Zhang worked on. And the cube also gives you an integral packing. It's dual to the octahedron, so maybe that's not surprising. And the cube arose independently in work of Kate Stange on constructing circle packings. If you are curious, the dodecahedron and icosahedron are not integral, but they can be made, but they're golden. So there exist configurations, all of which the integers, all of whose curvatures lie in the ring of integers of the golden mean. Which, by the way, tells you that the corresponding reflection groups, when you add the reflectors, are not arithmetic. So these are not arithmetic groups. So I really want integer packings. I don't want algebraic integer packings for this packing arithmeticity conjecture. Okay, what about the Archimedean solids? The cube octahedron that we spoke about, there's no E in cube octahedron, is integral. The truncated tetrahedron and the truncated octahedron are. The truncated cube is not, interestingly. The icosahedron, I don't know if you know these classifications off the top of your head. There's a great and small rhombi-icosahedron, the truncated dodecahedron, and the truncated icosahedron are all, again, golden. If you know that there are 13 Archimedean solids, so we have 3, 4, 5, 6, 7, 8, 9 so far. So golden, again, means their curvatures are all in the golden mean. There are a few more. The truncated cube that we discussed earlier, the great and small rhombic cuboctahedron, are not integral and not golden, but they're silver. So there are configurations so that all of the curvatures have silver integral bends, where the silver mean is continued fraction with all 2's instead of all 1's. I didn't make that up. It's Wikipedia told me. So they're called silver. They're not quite as good as... Do you have silver gates in your theory? Okay, and so that was 9, 10, 11, 12, or 11. Somehow there are 13 of them, so there are 2 more that are missing. The snub cube and the snub dodecahedron are the remaining Archimedean solids, and these are not even integers. There's some algebraic. You can make the curvatures algebraic, but the snub cube has cubic bends, and the snub dodecahedron has sextic bends. So that's it for Platonic and Archimedean solids. 2 more families, the prisms and the antiprisms. So the 3, 4, and 6 prism and the 3 antiprism are integral, and they're the only ones. I guess I could try to draw you a picture of a 3. Okay, if you ask me at the end, maybe I'll draw you a picture of a 3 antiprism. What you do is you take antiprism, you take two triangles, one on top and on bottom. So what's a prism? You have a triangle on top, triangle on bottom, and you just make squares, square faces all around. Antiprism, you rotate them a little bit, and then you make triangle faces like, you know, Bart Simpson's hair or something. You make, go all around. So this is really cheating because what is the 3 antiprism? If I take a triangle on top and bottom, I rotate and I glue in triangles at the faces, I get an octahedron. Okay, so this is not something new. That's why it's colored. So this is the same as the octahedron. How about a 4 prism? 4 prism means you take a square on top and bottom, and then you put squares around. That's a cube. That's not new. Okay. The 6 prism genuinely is a new packing, and the 3 prism is colored this way. So what's a 3 prism? You have a triangle on top and bottom, and what you can do is you can pinch that triangle's waist until it becomes a vertex, and now you have 2 tetrahedra. So this is the gluing, so the triangular prism is the gluing along a vertex of 2 tetrahedra, and that produces the same circle packing as the original Apollonian circle packing. So that's not new either. So among the prisms and antiprisms, the only thing new you get is this hexagonal prism. Okay. Another corollary of the proof is that the dual polyhedron in these examples is integral if and only if the original polyhedron is. I don't know if that's a general fact, but I suspect it should be. In fact, it should come from the arithmeticity conjecture. So the octahedron is self-dual, the tetrahedron is self-dual, the octahedron and cube are dual to each other. The dual of the cube octahedron is this rhombic dodecahedron we discussed. Then the other duals are triachus tetrahedron and tetrachus hexahedron. These are the Catalan, the last of the Catalan solids, which are integral. The duals of the prisms, if you have a prism, so you have an n-gon on top and an n-gon on bottom, well, the dual of that will have a vertex on top, a vertex on bottom, and some number of vertices around the sides, so that's a bipyramid. So the 3, 4, 6 bipyramids are also integral. And the dual to the antiprisms are called trapezohedra. So the 3 trapezohedra, which of course is a cube because the 3 antiprism is an octahedron, those are all integral. Now what I haven't written here, because I'm not brave enough to do it, is we think this is it. This should be the entire list up to these doubling, up to maximality. So in fact, the octahedron itself is not maximal, because the octahedron is the gluing of a square pyramid on top and on bottom along a face. Okay? So up to issues of maximality, we believe this is the whole list. Okay, so let's work out the cube octahedron a little bit more explicitly. I think I'm going to end a little early, and that's okay. So here is a cluster modeled on the cube octahedron, and now I've labeled it with the curvatures. As you can see, they're all integers. So again, around the 63 circle is a square, triangle, square, triangle, and the same goes all around. And when you pack this thing, that's the cube octahedral packing. A theorem with a little t means we're still writing up the details, but we're pretty sure it's going to go through, is this original theorem of Jean and myself goes through in this case. And what's very interesting, I mean, this is kind of the origin of our arithmeticity conjectures. And in all of these cases, every integral family that we found, it has this property that Peter discovered for the Apollonian packing. So the Apollonian circle packing, the Apollonian group, this infinite volume hyperbolic reflection group, if you take the subgroup of it which stabilizes a single circle, you get an arithmetic congruent surface group. In fact, you get something commensurable with SL2Z. And that happens in all of these examples, all of these infinite volume groups. If you look at the stabilizer of a single circle, you don't know what it is. It's a bunch, it's given to you by some matrices, and you have to go and work out what these matrices generate. But in every case, they generate congruence groups. So that's what allows us, plus the general counting techniques I described before, basically this theorem with Jean goes through in all the known cases. Okay, Jean, if you're listening, thank you for many years of friendship and your tutelage, and I thank all of you for listening.